A program receives more data than one memory buffer can hold. It crashes. Is that only a reliability bug, a denial of service, an information leak, or a path to code execution? The honest answer is, we need evidence. Exploit development is the disciplined study of how a vulnerability changes program state and whether that change can produce a security impact. For beginners, buffer overflows are a useful teaching model because they connect source code, memory layout, debugging, operating system protections, and secure design. This video explains those connections without creating a weaponized exploit. Our practical example uses a deliberately vulnerable toy parser in an isolated lab. We stop at reproducing a controlled crash, locating the missing link check, and verifying the fix. Never test unknown binaries, public services, or software you do not own without explicit authorization. Use disposable virtual machines, synthetic inputs, snapshots, and non-production targets. Popular low-level security explainers often succeed by making invisible memory visible. They animate small blocks, follow one input through a program, freeze the moment a boundary is crossed, and compare defenses one layer at a time. We will adapt those general teaching techniques, while every line, illustration, example, and scene composition remains original to CipherVibe. Here is the memorable analogy. Imagine a hotel with numbered rooms. A guest is assigned room 8, but the front desk mistakenly hands them a cart that keeps moving through the wall into rooms 9 and 10. The immediate problem is not that the guest is clever. The problem is that the system failed to enforce the room boundary. Memory safety works the same way. A buffer has an intended region. If a read or write crosses that region, neighboring state may be damaged or exposed. Which neighbor is affected and how much control the input provides determines the consequence. A buffer is a region of memory reserved for data such as characters, network messages, or file contents. The program must know how much space exists and how much data it is allowed to place there. MITRE's classic CWE 120 describes copying input into an output buffer without verifying that the input fits. Related weaknesses include stack-based and heap-based overflows, out-of-bounds reads, improper indexes, integer length mistakes, and missing string termination. A stack overflow may corrupt nearby local data, bookkeeping, or control-related state. A heap overflow may damage neighboring allocations or allocator metadata. An out-of-bounds read can expose data without writing anything. Do not assume every crash is exploitable or every overflow leads to code execution. First, determine the exact operation, direction, size, neighboring state, input control, repeatability, and process privileges. The root cause is a missing or incorrect boundary, not the debugger, the crash message, or the input pattern used to reveal it. For layers interact. Source code defines the data flow, buffer size, length arithmetic, and copy operation. The compiler turns that logic into machine code and may add protections such as stack checks, control flow protections, and safer runtime behavior. The loader arranges code, libraries, stacks, heaps, and mappings inside the process. Address space randomization makes useful locations less predictable. Non-executable memory, called DEP or NX in common platforms, prevents ordinary data pages from being executed as code. Control flow protections restrict where indirect execution may continue. These mitigations make exploitation harder, but they do not repair the underlying overflow. A crash, data corruption, or denial of service may remain. Mitigations are layers, not permission to keep unsafe code. Architecture also matters. Pointer size, calling conventions, alignment, endianness, and memory model change what the same source-level mistake looks like at runtime. That is why vulnerability research begins with the exact build and environment. Source review follows input from entry point to allocation, length calculation, copy, and later use. It is best when code is available and you want root cause clarity. Its limitation is human coverage. Static analysis can identify suspicious data flows and unsafe operations across a large codebase, but findings need manual validation and context. Fuzzing generates or mutates many structured inputs and watches for crashes, sanitizer findings, hangs, or unexpected behavior. Coverage-guided fuzzing is excellent for parsers and complex state machines, but a crash is the beginning of triage, not the end. Debugger analysis freezes execution near the fault and shows registers, memory, call stack, exceptions, and the instruction that failed. It is ideal for determining what was corrupted and why. Dynamic sanitizers add checks during testing and often report the invalid access close to its origin. They improve diagnosis, but are usually intended for test builds. Strong research combines these approaches. Review suggests hypotheses, fuzzing finds edge cases, sanitizers localize memory violations, and the debugger explains the concrete failure. Our fictional badge reader accepts a training record containing a display name. The parser reserves a small fixed region for that name, then copies the supplied characters without first confirming that the record length fits. In a disposable lab build, a short synthetic name works normally. A longer generated test record terminates the process under a memory sanitizer. The report says a write crossed the end of the local name region. That gives us a precise hypothesis. The parser trusts the record's declared length and copies more bytes than the destination can hold. We reproduce the failure with the smallest input length that crosses the boundary, record the exact build, sanitizer output, input structure, and expected behavior, then stop. We do not attempt to redirect execution, bypass protections, add a payload, or target another process. The practical lesson is the research loop. Establish a normal baseline, change one dimension, length, observe the fault, minimize the test case, and connect the failure back to source. The fix begins at the trust boundary. The parser must verify that the declared length is valid for the record and no larger than the destination capacity after accounting for any terminator. Prefer interfaces that carry both pointer and capacity, containers that track their own size, or memory-safe language features where practical. If truncation is allowed, make it explicit and handle the result. Silent truncation can create separate security or logic problems. Be careful with functions described as bounded. A limit can still be wrong, derived from the source instead of the destination, affected by integer overflow, or fail to guarantee string termination. For badge reader, the corrected parser rejects an oversized name before copying. A regression test confirms that the former crash input now returns a clean error. Additional tests cover an empty value, the maximum valid size, 1 byte above the limit, malformed length fields, and missing termination. Run static analysis, warnings, sanitizers, and fuzzing in the development pipeline. The durable fix restores the data contract and makes future violations observable. After confirming memory corruption, assess security impact without overclaiming. Ask what the input controls, only length, the overwritten bytes, or both. Identify the corrupted object and how the program uses it later. Determine whether the vulnerable path is reachable by an untrusted user, file, network message, or local account. Evaluate reliability across supported builds and architectures. Record process privileges, sandboxing, isolation, and whether a crash affects availability. Review stack protection, ASLR, DP or NX, control flow defenses, hardened allocators, and compiler settings. A memory error may produce only a controlled failure in one build and more serious impact in another. Likewise, a mitigation may block one exploitation strategy without removing information disclosure or denial of service. For disclosure, provide enough evidence for the owner to reproduce and prioritize the vulnerability while withholding dangerous operational detail until remediation and coordinated publication. Severity should reflect demonstrated impact and credible constraints, not the most dramatic theoretical outcome. The first mistake is testing software without authorization. Reverse engineering, fuzzing, or sending malformed traffic to a public service can create legal and operational risk. The second is using an everyday workstation. Unknown binaries and malformed files belong in an isolated, disposable environment with snapshots, limited networking, no personal credentials, and carefully controlled sharing. The third is disabling protections for convenience and then claiming the result applies to production. A teaching build may remove mitigations to make memory concepts visible, but real assessment must document the exact shipping configuration. Other mistakes include assuming a crash equals code execution, ignoring integer and termination errors, testing only one architecture, collecting unnecessary data, leaking crash dumps that contain secrets, publishing details before a fix, and writing a patch that merely changes the crash location. Keep test cases, symbols, dumps, and reports access controlled. Coordinate disclosure with the owner. Verify licensing, export, legal, and program requirements for the target and jurisdiction. This video is educational, not authorization or a weaponization guide. Here is the complete beginner workflow. Work only in an authorized, isolated lab. Record the exact source, binary, architecture, compiler, libraries, operating system, and mitigation settings. Establish normal behavior. Reproduce the failure with synthetic input, minimize the test case, and locate the first invalid read or write. Use source review for root cause, fuzzing for input coverage, sanitizers for early detection, and debuggers for concrete program state. Assess impact carefully, attacker control, reachability, corrupted data, repeatability, privileges, isolation, and mitigations. Do not equate a crash with arbitrary code execution. Fix the trust boundary with correct length validation and capacity-aware design. Preserve termination, handle arithmetic safely, prefer memory-safe abstractions, and add regression tests, warnings, static analysis, sanitizers, and fuzzing. Remember the hotel rooms, the important failure is the missing boundary. Exploit research explains what crossed it and why. Secure engineering rebuilds the wall so the same class of mistake is caught before release. Copyright 2026 CipherVibe. All rights reserved.